Hey guys, so this is a little bit of an introduction to why 7.1 matters and what are the big principles that we're dealing with here. In 7.1 we're dealing with what are called exponential, bad sloppy writing on that part, but exponential growth functions, okay? And when we're talking about growth that's exponential, we mean something where the growth over time is not linear, it's not a straight line. It's not like I'm adding $1 a day and I keep adding $1 a day. It means I'm going to add $1 the first day, I might add $2 the next day, then $4, then and so on and so on. This is going to continue to get bigger and bigger as I add a larger and larger piece each day. When we talk about them, they typically follow in this format. Let me give you a really basic example. Y equals 2 to the x. This is probably the simplest one we can talk about. It's the doubling function where every time we're going to multiply our last result by 2. And that's what this exponent does here. If you think about it, when x is 1, okay, it becomes 2 to the first. Well, 2 to the first is just 2. But when x is 2, okay, if I change this 1 to a 2, then it's 2 times 2, which is 4. Well, you might say, oh, well, it just went up by 2. Not a big deal, Mr. Welch. But if I let x become 3, okay, now I have 2 times 2 times 2. And we all know, we're good enough with exponents that 2 times 2 times 2. And we know 2 cubed is 8. See, instead of going up by the same amount each time, now it's going up by a bigger amount. And if I did it to the fourth, well, then I would end up with 16. To the fifth, I would end up with 32. So this is not going up a small amount each time. It's growing in how much it goes up by. It doesn't take long before we realize that we're going to end up with a very, very large result. And so if we were to try and graph something like this, some stuff that you'd need to know, okay, obviously 1 is at 2. Well, 0, well, anything to the 0 power, by definition, if I put a 0 exponent on something, the result is 1. So let's put a dot at 0, 1, and a dot at 1, 2, 2's at 4. So we can see it might look like a little bit of a straight line, but it's really not. And if I kept going to 3, 4, 5, 6, 7, 8, now, I'm going to have to stop the rate at which I climb as I go to the left. If we use negative exponents, okay, 2 to the, let's scratch that all out and make it negative 1. We remember that negative exponents cause reciprocation. This becomes 1 over 2 to the first, or in other words, 1/2, which means that I'm going to be right down here. Okay, and we can see this is starting to curve as we come back. Well, because we think about taking, when we go to the right, we keep doubling our answer. From 2 to 4, we doubled it. From 4 to 8, we doubled it. From 8 to 16, we doubled it. If we were to go in the opposite direction, meaning going to the left into the negatives, we would expect the opposite result. And it's true. As we go from 0 to 1, we're at 0, 1. As we go to negative 1, we get to half of 1. The next number would be a quarter, which would be really tiny down here. And so on. It's going to continue to get closer and closer to 0. But because we're dividing, we're never going to be able to divide this down to actual 0. And because of that, this line is going to follow the x-axis, trying to get infinitely close, but never actually touching it as it goes to the left. So it's going to trail to the left forever, but not actually touch the line at x equals 0, or y equals 0. So I'm going to draw on what's called a horizontal asymptote. This tells everybody in the world, hey, that's a boundary line. We're not actually physically touching. We're just going to get infinitely close. That helps us understand a little bit about the domain and the range when we go to evaluate these. The domain of an exponential graph, well, this graph does go forever to the left. No issues there. And even though it's very vertical, it is trailing to the right. It does continue to travel right. You ask yourself, mathematically, can I answer the question 2 to the 100th power? If I went all the way out here to 100, would the graph exist? The answer is yes. Now, you and I should probably never spend time trying to figure out what 2 to the 100th power is. It's a massive number. and it's going to take a long time to evaluate that. 2 times 2, yeah, at first it's pretty easy, but then it starts getting into multi-digit numbers, and it's large. And so I'm not going to spend my time doing that. But just knowing that it exists is important. What that means is that this graph does go forever in both directions, and so the domain is all real numbers. That's our fancy R for all real numbers. The range, however, does have a restriction. We can tell because as we go to the left, this thing just doesn't seem to keep dropping. The entire graph of the y equals 2 to the x lives above the x-axis. And so we would say that the range is y is greater than, but not equal to, never touches, so just greater than 0. All right. Exponential growth can be used for a lot of things. Among the things that we do use it for, we can also use it for interest, whether that's interest paid to you because you have a savings account or interest that you owe as you pay off a debt. That interest is accrued exponentially. So the longer we wait, the worse it's going to get. Or in the case of saving money, the better it'll get. So let me show you what that equation looks like. There are 2 versions of it. There's just the annual growth, just straight annual growth where there's no compounding. It's just, hey, something went up in value over time. So this doesn't just have to be money. It could be a population of coyotes or a population of rabbits. We know that they will grow exponentially if they're not slowed down by something else. But it equals the principal, which is the initial amount, times 1 plus the rate. Now the rate has to be as a decimal, so 5% is actually 0.05 here. All raised to the t as an exponent, t being time. Usually measured in years, but if we want to do everything per hour, we could do it in hours. But this is our growth formula. Then we have what's called compounded interest. And this is the one that will literally cost you money or save you money in your lifetime. Okay? It has just a small variation from the annual growth formula. We still start with the amount we have in our account will equal what we put in to begin with, our principal, times 1 plus the rate divided by the number of times it's compounded. So n raised to the n times t. Those are both in the exponent. What this means is how often is the bank checking to decide how much interest you earned? Do they check once a year? If they do, it's just annual growth. But if they check 4 times a year, well, then this n would be 4, and that's going to affect how much money we get in our interest. It'll be better than doing it yearly, but it just depends on how often. The more often, the better. Okay? It cuts your interest rate in parts because you're doing it more often than once a year, but you also, because you do it more often than once a year, you will accrue more interest over that same year or that same time span. So if you want to understand how finances run, your banking system works, how your credit card or your home loan debt accrues interest, this is how we do that. This is how it's calculated. And in another section, we'll talk about the most commonly used interest method, which is a continuously compounded interest, which is it's a really interesting problem. It's based on the idea of letting n go to infinity. And as we do that, it's very cool how we get a specific result. We'll see that in 7.3, but these are the ideas that we're talking about. Hopefully that helps you. And then there's homework help for doing the specific problems over on the side of the textbook. All right, good luck.